Okay. Or maybe he's watching online, and I need to check my email. I think there is such a person in one of my classes. So anyway, I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless this class. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So you guys have any questions before I get into it? I think we had the definition of matrix multiplication, and so I was going to try to talk a little bit about just some other properties of matrices, and more really just talk about some special terminology to make sure we're all on the same page. So like this is proposition 1.3.13, and it has some things like the transpose of the transpose is back where we started, right? Or 2, the transpose of a product, right, is the product of the transposes in opposite order. 3, we can pull a constant out of a transposition and nothing happens to it, right? And of course, the transpose of a sum is the sum of the transposes. All right, so this is, you guys are probably like, I know all this. Good. Can you prove it? So I'll prove one of these. Which one do you guys want me to prove? Student's choice. Two? Good choice. So AB parentheses transpose, we want to calculate that. So we're going to do other parentheses out here, okay? IJ. Let's look at the ijth component of that. So now by definition of the transpose, that's A times B JI, right? Because remember the definition of transpose is that we flip the indices, right? So did I ever write that in here? Maybe I haven't, I don't remember. Just to be clear, definition A transpose IJ is equal to AJI, right? That's the definition of transpose. So it takes an m by n matrix and makes it into an n by m matrix. All right, so we've got ABJI, right? And then, by definition of matrix multiplication, that's the sum over K of A JK B KI, right? So, definition of matrix multiplication. Now, I guess if I wanted to be a little bit more precise, and I probably should, what are we assuming about A and B here? Let me do my due diligence. Let A be an element of R m by n, and B be an element of R n by, let's say, Q, to mix it up. Okay? So K, what should K sum over? K equals 1 to what? N. Very good. Now what can I do? Well, notice that AJK and BKI are just numbers. Therefore, they commute. So this is the sum, K equals 1 to N, of BKI AJK. Property, well, let's just say multiplication in R commutes. And I'm assuming that R is a quote-unquote commutative ring with unity here. All right. Could be real numbers. Could be a lot of things. Now, next step, use the definition of transpose again 2 times. So this is B transpose IK A transpose KJ. All right. And then we use the definition of matrix multiplication. See, that's exactly B transpose times A transpose, the ijth component of that, right? So here's the definition of transpose, and this was definition of matrix multiplication. Thus, A, B, transpose is equal to B transpose A transpose as the above holds for all I and j. So there you go. That is a proof, an index theoretic proof of the so-called sock-shoes identity for matrix multiplication. Right? What other matrix operation works like this? Do you guys remember? Inverse, very good. Right. The inverse also works like this. Let's see here. So, let's see if I can talk about that for a minute. Definition A in, let's say, f n by n. No, I don't need. I'm still in R. I'm my bad. A in commutative ring with unity again has inverse, which we denote A inverse if A times A inverse is equal to the identity matrix and A inverse times A is equal to the identity matrix, right? And we can prove, in fact, that either one of those conditions suffices, all right? If either A times A inverse is the identity or if A inverse times A is the identity, either one of those makes the other happen. This can be proved, all right? So a more like logically efficient definition for inverse might be just that, just one of those. Now, of course, this begs the question: what's the identity? Right? And we know what that is. Ij, the component of the identity is the Kronecker delta, right? 1 if I is equal to j, 0 if I is not equal to j. So this is the identity matrix, right? And you notice I'm a little bit ambiguous here. Like, how big is this identity matrix? Well, it depends on our context, right? If we need to be clear about the context, we could use notation like this, right? I2 is 1, 0, 0, 1, or I3 is 1, 0, 0, 0, 1, 0, or 0, 0, 1, like that, right? And now is a good time as any to notice something about the identity matrix, which is that it's concatenation of the standard basis, right? So like I2 is actually what? It's like E1 with E2 here, right? And I3 is E1, E2, E3, like that, yeah? So we can build the identity matrix by just gluing together the standard basis. This is still true in n dimensions, right? The n by n identity matrix is E1 concatenated with E2, dot, 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 concatenated with En, right? Now you guys reminded me that the property matrix multiplication, like A times B inverse, what was it equal to? You told me B inverse times A inverse, right? We could prove that. That's true. That I also call that the sock shoes rule, right? The question or no? If you have a question, feel free to interject. Now the identity matrix, of course we can prove that the identity matrix times any other matrix gives you back the matrix again, right? Assuming that the matrix is, multipliable, right? Like, is a theorem. If we have x times the identity matrix, well then that's equal to x, all right? So here, let's, for context here, let's let this be like m by n, and we'll let this be the n by n identity, right? Okay. So that's a theorem that we could prove. And I think before I prove that theorem, I want to remind you guys some like sort of mechanical lemmas about how multiplication by the standard basis works, and then we can use those, right? So like preamble to proof, let's call it, okay? So these just, so what happens if we have a matrix A times EI? What was that equal to? And on the other hand, what happens if we do like, you know, E bar J times A, like that, transpose here? What is a matrix times the column vector? Excuse me, listen to me. Matrix times standard basis is what? This is equal to, remember, column I of A, right? So if we multiply by standard basis, we get the column. And this, on the other hand, is row J of A. And if we sandwich the matrix in between, like EI bar A, EJ like this, with the transpose over here, then that's going to give us A IJ. So we'd actually select the IJth component. Listen, guys, the reason I'm using a bar on the one E and not on the other is because I want to allow the possibility that the matrix is like rectangular. So I need a different dimension of the thing multiplying on the left versus on the right. So like here, I'm supposing like E bar I is an element of Rm, and EI is an element of Rn in my current discussion here, okay? Do you guys know this, or do I need to like explain this more? Okay. I do have proofs of these in the notes. They're not especially exciting, but they all can be proved, all right? So if we know these things, we can use these things. So going back to my proof, here's the proof. I have x times I, right? But that's x times I is E1, E2, En. So there are different methods of proof we can use. You see, we could use component level proofs, or we can do column level proofs. Sometimes column level proofs are much easier to see. They're a little bit less cumbersome. The most cumbersome form of all is plus dot 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 dot, write out a giant box of numbers and try to work through it like brute force. That is just, well, to be honest, that's the dumb way to do it. So don't do that. Unless you can't figure the other way out and just do something, right? Something is better than nothing, but anyway, here we go. So let me stop wasting precious class time on nonsense. So here we get that. What's this? This is the row by row multiplication rule, right? This is one of the properties of matrix multiplication. If we multiply a matrix times another matrix written in terms of the concatenation of its columns, we can multiply column by column. This is the column by column matrix multiplication rule. And then, what do you got? Well, you got column 1 of x, right? All the way on out to column n of x, also known as, well, x. So I just wanted to sort of exhibit a column proof for you guys. There it is. So I think like the last problem in your homework, I encourage you to get to know some of these things better. There's a problem in your homework where you're going to kind of need to do these kinds of calculations to understand how these can be used to build the matrix units. And then, more than that, the problem explores what does it mean to multiply a matrix times a matrix unit, you know?
They're very different from each other in terms of how you explain.
Howdy.
Hey, does Violet pack up early in your class?
Is your class over?
No, my class is finished. You know, it was in the last, and it finished it a while ago.
Did she pack up early?
She packed up
How
too early.
dare she? I tell you. The nerve of some people. Anyway, okay, sorry. Mental note, must close door before teaching. All right, so anyway, so one of your homework problems, I'm actually letting you guys homework, you're going to explore, what does it look like to take Eij times A? What's this mean? Means what? And what if we take A times Eij on the other side, right? What does that do to the matrix? All right? So I'm going to let you find that out. Here I'm assuming they're all square, so like we could multiply the same Eij on both sides, okay? All right. So if this is completely foreign to you, you should read the section I talk about bases, all your bases are belong to us. Like, read through that. Try to understand it. If you don't understand it, come ask me questions about it, all right? All right, so reminder, if we have a 2 by 2 matrix, A, B, C, D, right? Did I ever move? I didn't move. If we have a 2 by matrix, A, B, C, D, what's the, man, I'm very bad at this. Whoa, dizzy. The inverse of this, remember, is 1 over AD minus BC times D minus B minus C, and then A here, right? If AD minus BC is not equal to 0. That's actually not quite true. In the context of a commutative ring with identity, I really should rewrite this. Actually, this becomes AD minus BC inverse times D minus B minus CA. So this is for a for field, but this is for a commutative ring. Let me actually be explicit about the difference, okay? Because I think some of you may not have any idea what I'm talking about at the moment, and you have some homework on it, so let's, talk at least a little bit about it. So, for instance, Z3 is the set 0, 1, 2 with the following multiplication table, right? Two times 2 is 4. 2 times 2 is 4, but mod 3, 4 is equal to what? 1, right. So if I have, for instance, the matrix, let's say 1, 2, 1, 1, right? Then if I tried to invert this, and this is a matrix in the Z3 2 by 2 matrices, okay? Then the way that would work, or try to work anyway, would be like 1 minus 2 inverse. I flip the diagonals, which is kind of a non-event here. My minus is on the off diagonals, like that. And so what I have is minus 1. The minus 1 is equal to 2, by the way, mod 3. So I actually have 2 inverse times 1 minus 2. Minus 2 is what? Minus 2 is add 3, it's 1. Minus 1 add 3 is 2, all right? 1, I have that. What is 2 inverse here? 2 times what is 1 again? See, 2 times 2 inverse is what should be 1. What does that make 2 inverse mod 3? 2, right? So the inverse of 2 mod 3 is itself, yeah.
So for the definition up there, when you changed it to suit a commutative ring in general, the difference between a commutative ring and a field is that not everything in a commutative ring has inverses, right? We talked about this last class, I think.
Yes.
So does changing the notation like that really change anything if there is no...
Yes, because it is not permissible to write 1 over Like we do not write 1 over something for a fraction in an abstract ring.
Okay.
Partly because we also deal with non-commutative rings, and then like the fraction notation is just troublesome.
Right. Okay.
You know, because A over B, like is that A times 1 over B, or is it 1 over B times A?
Right.
So like the fraction notation sort of assumes commutativity, and it's just generally not done. Like if you want to make like Dr. Sprano like unhappy, use fraction notation in like Z mod 5 or something. Like, no, don't do this. So instead, we write 2 inverse rather than 1 over 2,
Okay.
with the understanding it's the number that when multiplied by itself gets you back to the multiplicative identity.
Okay. But for a definition in a commutative ring, should we add like if it exists, AD minus BC inverse?
Well, yeah, for a commutative ring, and then I think I lost my train of thought here, where, you know, AD minus BC inverse exists, right? So it doesn't have to be the case that it exists. For instance, what example did I have? I have not numbered any of my examples. Well, I guess I didn't do any examples yet. This is example 1, and here's example 2. All right. And I think I'm digressing wildly from my course plan at the moment, so my apologies, but it is all in the service of making your homework more understandable, so there's a method to my madness. So if I'm working in Z6, that's a trouble. That's not a field, because in Z6 we have 2 times 3 is equal to 0, but neither 2 nor 3 is 0. So those are called 0 divisors. They don't have inverses. But in Z mod 6, notice that like 5 times 5 is 25, which is 1. So therefore, again, it's its own inverse. And trying to think, 3 times 3 is, 3 is 0 divisor. I think yeah, that's it. That's the only invertible elements in Z6 are 1 and 5. All right. So if I write down a matrix like, 2, 1, 4, I don't know, 3, then if you look at the determinant of this thing, right, 2 times 3 minus 1 times 4, well, that's 2. So A inverse does not exist for this guy. Right. All right. So sorry, I do try to prove things in here for the most part, and I'm kind of just giving you some high points of a longer discussion. So that's not ideal. It's not what I try to do in here. So let me try to get back on track. So in chapter 1, there really are a few special kinds of matrices that we need to know about. The one, of course, is the identity matrix is important, obviously. I want to introduce you guys to the concept of matrices with numbers from things other than reals or complex or rational, right? You can talk about matrices with numbers from Z mod something, all right? But then, of course, we talked about inverse. We could talk about the inverse of a matrix. We could talk about the transpose of a matrix. But then there are special kinds of matrices, right? Like there's diagonal matrices, triangular matrices, symmetric, anti-symmetric, nilpotent, right? We'd like to understand these terms, yeah? So do you guys already know all those, or do I need to define them? I think I can safely assume I need to define them, right? Yeah, okay. Because these are the things that our examples tend to be built from. Matrices of a special type. That makes it interesting, usually. So here we go. Definition. Let A and N be square matrices over a commutative ring with identity. Again, it's almost, oh man, could have been somebody. All right, I'm gonna, haha. There we go. So, if A transpose is equal to A, this is also garbage. Oh, come on. That should have gone in. Then what is A called? A transpose A equals to A. This is a symmetric matrix, right? So some of you had Majeric, right? He does talk about symmetric matrices, right?
He does.
Yeah, okay. What if there's a minus there instead? Anti-symmetric, right? Now, 3, if there exists, let's say, k in the natural numbers such that n to the power k is equal to 0, yet n to the k minus 1 is not equal to 0, then n is nilpotent of order k. For if A looks like, you know, A11, A12, da da da, A1n, ANN, zeros down here, right? Can we write that in terms of matrix units? What would that look like? This is what? The sum over what? I less than or equal to j. Yes? Those are the kinds of indices that we have, right? The row index is always at most the column index, and usually less than it, right? It's equal to the column index on the diagonal, but otherwise we have strict inequality there, right? So I could just write this, Aij, Eij. There's a index-based formula for an upper triangular matrix, yeah? And likewise, if we had, you know, if you go with I greater than or equal to j, you get what? A lower triangular matrix, right? And of course, often interesting, if you have A is just equal to the sum I equals 1 to n of A I, E I, then A is diagonal. All right? So in Dr. Majeric's class, did he talk about block multiplication at all? Making a matrix in terms of like submatrices? Like it's almost a matrix of matrices.
Is it the one where you have like a, I think that's it.
So this isn't so much a type of matrix as a type of like another way of looking at multiplication, maybe you could say. So I'll just deal with like a particular case of it. So if I had A looks like, say, M, big N, L, oh man, bad choice. Let's try this again. if I had A is A1, A2, A3, A4, all right? And if I had B is B1, B2, B3, B4, all right?
Dr. McGarrett definitely went over this.
Okay, good, good. So, and these are all themselves matrices, right? Then you remember what happens when you multiply these? How's it go? Like what's A times B? So like we multiply them as if they're numbers, but we have to be careful because they're matrices so they don't commute, right? So like we do the usual thing, A1, B1 plus A2, B3, and then like A3, B1 plus A4, B3, A1, B2 plus A2, B4, A3, B2 plus A4, B4, right? But the thing is, A1, A2, A3, A4, these could all be like 10 by 10 matrices, right? This could be a 20 by 20 matrix, but the point is that you can use what's called block multiplication to parse the multiplication in terms of the multiplication of blocks, providing that the blocks have appropriately matching sizes, right? This is block multiplication. Perhaps the most interesting possible case in this whole story is when we have block diagonal matrices, right? And those look like what? That means that A looks like, A1, A2, A sub k, let's say, and it's 0 elsewhere. So there's matrices on the diagonal blocks of them, right? But otherwise it's 0. So these are all important ideas. All right, so I think with that I've at least said some words to you about everything in chapter 1. Of course, it would be good for you just to read through and kind of absorb the rest of what I haven't said. Yeah. Block diagonal matrices are super nice. Like, what's the inverse of a block diagonal matrix? Inverse of all the blocks. And if even one of the blocks doesn't have an inverse, game over, right? The determinant of a block diagonal matrix is the product of the determinants of the blocks. We learned that as well, right? Yeah. So with that, we move on. So systems of equations. I think is my chapter 2. And I think this probably will, for the most part, feel like, more familiar, perhaps. So you guys know the usual story. We have A1, 1, x1, AM1, x1 equal to B1, and this story goes on until we get to AM1, x1, AMN, xn. That was supposed to be an n, my bad. And that was, good grief, what's wrong with me? Look at that. 1, 1 to M1. No? No, that's 1n, right? Duh. My bad, not you guys. So here we're looking at m equations and n unknowns. And you guys remember the story. We take this and we replace it with the coefficient matrix concatenated with the inhomogeneous term. This is the augmented coefficient matrix, right? And what did we do? Do you guys remember? Of course you remember this, yes. We did, what are those things called? Row operations, right? We learned that if we calculate the reduced row echelon form of the augmented coefficient matrix, this allows us to read solutions to star nicely in a standard way, right? So what's some terminology I should remind you? The system is said to be consistent if the solution set is non-empty, right? The system is said to be homogeneous if all of the b's are 0, right? If there's even one b which is not 0, it's said to be non-homogeneous, right? Like here's, and of course then the other thing that's much nicer to look at this is a times x equals to b, right? So this is the vector form of the system. And we have various theorems, like theorem if a statement of the theorem. There's a theorem I was going to show you guys because it's super easy and a nice demonstration of the matrix technique that I hope you would appreciate now. You might not have appreciated it as much in the 221 context, but here perhaps enough time has passed that this kind of argument will be appreciated more. So if A is an element of, let's say, f m by n, and b is not equal to 0, suppose a times xp is equal to b for some xp not equal to 0. Well, I think that may not be necessary. I mean, like, if xp is 0, okay, I'm gonna call an audible here. I don't think we need this. Suppose axp for some xp. Okay, there we go. And then rather any solution of ax equals to b has form x is equal to xh plus xp, where a times xh is equal to 0. Why is there an h there? What's the word we have in mind? H is for homogeneous, right? Homogeneous. So any solution to the system ax equals to b can be written as the sum of a homogeneous solution and that one particular solution that you already got. Can we prove that? Right? Well, here's how the proof goes. It's only like a line. Suppose that we have ax equals to b and axp is equal to b. Then notice xh equals to x x minus xp has a times xh equals to a times x minus xp, properties of matrix multiplication, ax minus axp, yeah? Hey, but that's b minus b, is it not? By assumption, which is 0. Thus, x is equal to xp plus xh with axh is equal to 0. you notice that the structure of this argument doesn't really require that B is non-zero at all. This is really just a theorem about the solution set to a linear system, be it homogeneous or not. The general solution is formed by any given solution plus an arbitrary solution in the null set of the matrix. You guys remember, this condition right here says that XH is an element of the null space of A, yes? Remember that? Null space of A is a set of all vectors that, when multiplied by A, go to 0. So I thought that was particularly nice little theorem. All right, so so it turns out that the row reduction stuff that we did last semester still works in a larger context than we already have. Like, you can still do row reduction just as we have if you're working over like some other field. But I think it would be healthy for us to work some examples like that so you can appreciate the difference, yeah? So let's do some row reduction examples just to get back in the swing of things and to remind ourselves how the solution set's constructed and all that, right? So before I do anything, wild and crazy like Z mod 3, let me just do something over the reals, yeah? So example 3, how about we want to solve x1 plus x2 plus x3 plus x4 equals to 1, and minus x2 plus 3x4 equals to 0. Well, I want to find the solution set to that system of 2 equations and 4 unknowns. So here's what we do. We write down our augmented coefficient matrix, 1, 1, 1, 1 with a 1, and you got your 0, minus 1, 0, oops, 3, 0. All right, there's my A, B, so to speak, right? Then what? Well, I think we just need, pretty much, how about this? I just do row 1 plus row 2, right? Then that gives me 1, 0, 1, 4, 1, 0. If you guys don't mind, I'm going to do something very sketchy and do 2 things at once. Don't tell Dr. Majeric. Let's see here. Actually, this kind of seems, I bet he does this. He's pretty chill. That, my friends, is the reduced row echelon form of the augmented coefficient matrix, right? So this means what? This means that x1 is equal to minus x3 minus 4x4 plus 1. And x2 is equal to 3x4 plus 0. Yeah. So solution set looks like a minus x3 minus 4x4 plus 1, comma, 3x4, comma, x3, comma, x4, such that x3 and x4, they are keeping it real. There you go. And after a moment's introspection, you see that we can rewrite that as 1, 0, 0, 0, plus the span of, in fact, minus 1, 0, 1, 0, and minus 4, 0, oop, my bad, 3, 0, 1. Identify then that this is nothing more than the null space of A, and this right here is a particular solution to the system. Yeah?
Wouldn't it be
Uh-oh.
negative x3 minus 4x4 minus 1?
Nope. Because this row right here means that x1 plus x3 plus 4x4 is equal to 1. So I'm solving that for x1 to get to here, So it's the usual song and yeah, it's fine. So this exemplifies the theorem we're just talking about, which is that a system can be written as the sum of a particular solution and a homogeneous solution. Here I'm just expressing all possible homogeneous solutions as a span, because we can, right? So a particular solution will have the form, that's wrong. The general solution is like this plus C1 times that plus C2 times that, right? There's infinitely many solutions. In fact, there are 2 parameters in the solution set, right? Why are there 2 parameters in the solution set? Because there are 2 non-pivotal columns, right? Every non-pivotal column gets you a parameter in your solution set. And because we're working over an infinite field, we have an infinite solution set, right? What happens if we change this example a little bit and say same numbers, but now let's say it's in Z7? What if this was instead in the context of Z7, which of course is 0, 1, 2, 3, 4, 5, 6? So then, like your solution, the same steps work actually, right? Because we never divided by a number that we have to think hard about. We only did addition and subtraction, so that all works the same for modular arithmetic. And like long story short, over Z7, we'd have the same solution set, but the solution would look like, 1, 0, 0, plus, let me write down like a typical solution, C1 times minus 1, 0, 1, 0, plus C2 times minus 4, 3, 0, 1, where C1 and C2 are elements of Z7, right? So like, what's the cardinality? What's the size of the solution set? Let me use some kind of clunky notation. What's the number of things in the solution set? Can you count them? Of course, we could change like the -1 to a +6 and stuff like that if you wanted, but that's not required. We allow for multiple representatives of the different modular classes. Like, I'm not going to take points off if you write your answer in terms of -3 when it's just as good a 4 would do, right? Because -3 plus 7 is 4, so -3 is equal to 4 mod 7. I don't penalize you for like leaving numbers in terms of negatives unless I specifically said leave all your numbers in terms of positive residues as to reduce the load of my grading. I'm not playing poker with you guys. 2 reasons. 1, I can't read you. 2, I don't know how to play poker. But so if you look at it, since there's 2 parameters, you'd have 7 to the power 2. You'd have 49 solutions here. This cannot happen over an infinite field. What if we're trying to do like row reduction? Let's say, final example for today, example 4. Suppose you want to do a row reduction. You guys pick. Do you want to work in Z5? Z5 is nice. 5 is a nice modulus to work in. So let's try to look at, let's see here, 1, 1, 1, 0, 3, 2, 4, 1, I don't know, 3. All right, and we'll just do that. Let's try to row reduce this mod 5. So we start out the usual thing, right? 1, 0, 3, 0, 2, 1, 0, 1, 0. I just subtracted the first row from the second. Then, okay. Now I want to do something interesting. I want to multiply the second row by something. I want to change this 2 into a 1 mod 5. How do I do that? 2 times what is equal to 1 mod 5? 2 times blank is equal to 1 modulo 5. Three, very good. So 2, in other words, 2 inverse is equal to 3 in Z5. So if I do 3 times row 2, that would bring us to 1, 0, 3, 0, 1, 3, 0, 1, 0, right? And then I can, let's see here, I guess I'll do finally row 3 minus row 2, 1, 0, 3, 0, 1, 3, 0, 0, minus 3, right? Which is equal to 1, 0, 3, 0, 1, 3, 0, 0, 1. We can rescale that. It's not equal to, that's row equivalent, right? And so then you can just, like, you know, subtract the 1 off the top and you'd get 0, 0, 1, 0, 0, 0, 1. If that makes sense to you guys. So that would be an example of a row reduction in Z5. What does this mean? There's like 2 different ways to interpret it, and then we'll stop for today. First of all, what does it say about invertibility of this 3 by 3 matrix over Z5? Is it invertible? What do you think? I see a yes, because we row reduced. We got the identity matrix, which means it's row equivalent, whatever that means, to the identity matrix. We'll talk about row equivalence and the column correspondence property, all that next time, okay? So there's that. But here's a different way of looking at it. What if we looked at this as the augmented coefficient matrix for 3 equations and 2 unknowns, in the sense that we're looking at this? What can you tell me about that system? It's inconsistent, right? Because we reduced it and we got the 0 equals 1 equation in our last row. So almost everything you guys already know for fields still is true over Z mod a prime. If it's mod a prime, it's a field. If it's not a prime, it's like Z6, and that's outside our scope. That's a Math 422 thing, all right? But here we can pretty much, the major difference, and I spell it out in detail in the notes, is that the size of the solution set, the cardinality of it, depends on the size of the field. If it's infinite, and you've got one or more parameters, it's an infinite solution set. If it's a finite field, then the number of parameters, like the size of the field to the number of parameters, power is how many solutions, like we had over here, 7 squared, 49 solutions. So anyway, we don't do too much. We don't work with Z mod n that much in here, guys. I just want